Welcome everybody to the third week of the Parallel Programming Concepts course in OpenHBI. In this week we want to talk about shared memory parallelism, especially about ways how to program such systems. In the last week, the main topic we discussed was the question of concurrency. So we discussed the idea of having concurrent activities inside an application. Concurrent means that we have multiple activities progressing at the same time. And depending on the parallel hardware we may have available or not, we can then map these concurrent activities to processing elements and execute them in parallel, which brings us hopefully some speed up or scale up. When we have the situation, it turns out that parallel programming, as the title of this course says, is actually concurrent programming, because we now need to consider different effects and problems that may arise from the fact that we have concurrent activities running on one system with a shared memory. In the last week we discussed some of these problems, for example, race conditions and the protection from race conditions by the means of critical sections, semaphores, and mutexes. We also discussed advanced synchronization concepts in general, such as monitors or reader-writer locks. And all these different tools give you a possibility to deal with concurrency, to avoid race conditions, and to make your parallelized program, your concurrent program, in a way that you have predictable results regardless of the execution mode. In this third week of the course, we now want to move a little bit more into practice. So the idea here is to quickly cover different programming models that exist in reality and in practice that target shared memory systems. So in this week we only deal with shared memory parallel hardware, while in the fifth week we will then focus on shared nothing parallel hardware. Given the fact that parallel programming and parallel programming for shared memory systems is a very interesting topic at the moment for many industries and also for research. There's a lot of solutions out there, a lot of material, and you could basically spend a whole OpenHBI course only covering the different programming model ideas. Therefore, you will see that the content in this week is rather short and condensed, and we recommend you to also relate to the optional coding exercises we give you and to the related reading material in order to get more details in one or the other approach. So please take the content in this week as a recommendation and as an overview of how you can tackle parallelization in a shared memory system, so that you then have an initial guide to go through the different ideas and approaches that are available out there. When we look into parallel programming for shared memory systems, we have three basic classes of expressing parallelism and concurrency in your code. The most oldest approach, or the most traditional one, is the so-called process model, where we take operating system processes as a concept and express our parallelization, our concurrency, by creating multiple processes. When you take a process as an operating system concept, it has the inherent notion of dedicated memory. So each of the processes in your running computer system has its own memory region exclusively available. If you now want to do shared memory parallelism based on processes, you basically need to create shared memory regions between these processes. This is something that is supported in all major operating systems, for example, by the idea of memory mapped files. And this allows you to get a very coarse-grained, rough parallelization strategy where you have different processes only synchronizing from time to time, but most of the time computing on their own local memory regions. The second, maybe most prominent approach for parallelization in the shared memory world are threads, or sometimes they're also called lightweight processes. The idea here is that you have a single operating system process, and in this process, in this application, you have multiple threads of execution. So we have multiple control flows going on, although all of these threads share a common address space. By having a common address space, you come into the situation that you may have global variables that are shared between the threads. The access to these global variables must be synchronized, must be protected in order to avoid race conditions. And if you want to have local storage per thread, there's typically support for so-called thread local storage, TLS, which allows you to have a dedicated little piece of memory per thread. In this week, we also want to introduce to you a third idea of dealing with parallelism in the shared memory world, which is the most latest one and meanwhile also a very common one. This is task parallel programming. Task parallel programming is an extension of the thread idea. So you take again a given operating system process, and inside this process you may have multiple threads. With task parallel programming you are now able to express your concurrency in a more fine-grained way. So you define little pieces of work that may run in parallel, and these pieces of work, these tasks, are then dynamically mapped to a given number of threads inside your process. What is the advantage of this? The advantage is that you become independent from the number of threads that is actually instantiated inside your process. Let's consider you have either a 2-core system or an 8-core system. When you do explicit multi-threading, you come into the situation that you explicitly create either 2 or 4 threads and then distribute the work over them. While in task parallel programming, the idea is that you define as many fine-grained tasks as you can get, and then all these little fine-grained tasks are dynamically mapped to an appropriate number of threads for the particular system. So in a 2-core system, you may want to create only 2 threads, while in the 8-core system, you want to create 8 threads in order to get the maximum level of parallelism in the execution. So these pictures show you again the idea of the 3 different concepts. You see that it's getting more and more fine-grained. So with concurrent processes, we have an explicitly shared memory, while with threads and tasks, the shared memory is automatically given. You can have global variables by default in the programming languages, and now you need to synchronize the access from the different either threads or tasks to the shared memory in order to avoid any kind of race condition, deadlock, lifelock situation that may occur. Process-oriented and thread-oriented parallel programming is typically part of an operating system curriculum, so we will not go into too much detail here in this course, while we will spend most of the time with the task parallel programming. So let's have a short look, or maybe a repetition if you already know these things, about thread parallelization. So how can we express concurrent activities and parallel execution of these concurrent activities based on threads? The major standard in this area is the pthreads API, which is a part of the larger POSIX specification. POSIX is a programming interface, an API that is offered by all Unix-alike operating systems. So the idea of POSIX is that you get portable code for different flavors of Unix operating systems, either it's Linux or Mac OS or HPUX or Solaris. If you write a program that only relies on POSIX API, you can port the source code between the different architectures. And one part of this POSIX specification is pthreads, POSIX threads, and this gives you a minimum amount of functionality in order to deal with threads as an execution resource of the underlying operating system. The first part of this API are management functions in order to create or terminate threads. The second part are synchronization functions, which allow you to implement critical sections. For this, pthreads offers you a mutex primitive where you can create a binary lock, which can ever be taken by a thread or released. And based on this, you can then have further more elaborated synchronization primitives being implemented. Pthreads also offer condition variable support, and in extended versions of pthreads, you also have support for barriers or semaphores. Here's a small example for pthread code. You see that there's a main function, which is the main entry point in a C program, and this main function then creates a couple of threads with the pthread create call. You see that the number of threads is given as a constant here, so this is actually fixed, which is bad if you want to write code that should be ported amongst different platforms. We hand the name of a function, or more precisely a function pointer, to the pthread create function, and this gives the pthread create call the information of where the code is situated that should be run concurrently. The print hello method here in this example then performs some kind of activity and then at the end calls pthread exit. You could avoid this call by just returning a function result, which would then express the result of this thread execution. And the operating system will now make sure that your print hello function is run concurrently to your main function. If you have a parallel system, if you have multiple cores, both the main function and the print hello function may run even in parallel. At the end, we have a pthread exit call also in the main function in order to clean up all resources that are left over. With the management capabilities for threads, the next question is how do you synchronize the different concurrent activities that may run in parallel? And the typical method in pthreads is the join call. You have pthread join, which allows you to wait for the termination of another thread. So in the graph here, you see the typical pattern of how multithreading works with pthreads and other thread libraries. You have the main application thread, which is automatically started by when your process starts and your application starts. And this main thread then creates a couple of more threads, for example, by pthread create. These threads do their own activities, their own concurrent activities. And if you have parallel hardware, they will run in parallel because the operating system tries to distribute the given load of existing threads to all the available execution resources. At some point in time, the thread will be finished with its work, will either do an implicit or explicit call to pthread exit, and the main thread can wait for this call by the pthread join call. And this allows you now to have a forking of different parallel activities, explicitly created parallel activities, which then join again at a particular point in the control flow, and after this point you can continue with some kind of serial action. You see another example in C code. We have again a main function that is the entry point for our application, and we again create a number of threads in a loop, and we store the handles to these threads in the thread array, and we hand over the function pointer to the busywork function, which is the piece of code we want to execute concurrently in all our created threads. The difference to the example before is that we now have a second part in the main function, which is a loop that joins on all the created threads. So the main thread basically spawned a lot of concurrent activities and then waits in a loop that all of these activities terminate again. So this fork join model is a very common pattern in parallel programming, especially in the shared memory world, because you may have serial parts in your application, as we discussed in the discussion of Amdahl's law, and these serial parts then happen before or after you forked and joined on your parallel activities. When we talk about shared memory concurrency, we automatically have to deal with the problem of race conditions, and race conditions must be avoided by implementing critical sections. The pthread answer to this is the support for mutex primitive. So with the different API calls around the mutex idea, you can manage, create, and wait for locks. Pthread mutex init allows you to create a mutex resource, which is unlocked by default, and this becomes a resource of the surrounding operating system process. With pthread mutex lock, one of the threads can now wait to acquire the lock. This is like a binary semaphore, so the call will only return when you actually got the lock. There's another version of this call with mutex try lock, where the call always returns and you have to check by yourself for the return value whether or not you got the lock. The counterpart for mutex lock is mutex unlock, which allows a thread that already acquired a lock successfully to release it again. This leads to the fact that another thread waiting in a mutex lock call can now be woken up. And if multiple of such threads are waiting for the lock, the operating system decides which one will wake up first. So there is no predefined order, but this is an implementation detail of the operating system and relates to questions such as scheduling and prioritization of threads. Here's another C code example. Again, our main function, the entry point for the application. And here we see that as first activity in this toy example, the main thread is grabbing a lock. Since there is no other activity, no other thread in the code, this mutex lock call will succeed instantly and will return immediately. Then the main thread creates a couple of threads. And these threads have the function the_thread as their implementation. And in this implementation of the thread functionality, we see that the first activity is a mutex lock call on the same mutex variable. Since this mutex variable is a global variable, the thread implementation can immediately access it. So this is the idea of shared memory synchronization. But this mutex lock call will now block because the main thread is still holding the according mutex. After this creation attempt, there's a never sleep here for demonstration purposes if you run this code on a console. And then you see that there's a mutex unlock call. So in the next step, the main thread is releasing the mutex. And now all the different created threads waiting for this mutex are candidates for being woken up. The operating system will choose one of them. One of them will get the lock, will execute its critical section, and afterwards will unlock the mutex again so that the next thread can run this piece of code. After the finalization of all the threads, which is checked by a pre-thread join call again, the main thread then destroys the mutex resource, since this is a process resource, and then terminates. We recommend you to take a C compiler and play around with this code a little bit to get a basic understanding of how mutex synchronization and threading works in a real programming language. Since the POSIX API is specific for all Unix-alike systems, one of the interesting questions is now, what about Windows? And in Windows, we have different counterparts for the given POSIX functionality. So everything that we know from pthreads and POSIX is also available in Windows. You see here an example in this table. So mutex-based programming, thread-based programming is a standard concept in all of these systems, and you can write portable code that is in Windows code, in the Windows case, is portable between the different versions of Windows. The remaining question for multi-threading is now, what about high-level languages, stuff that goes beyond native code, for example, Java and .NET languages. And in this world, you typically have a representation of the underlying thread concept from the operating system. So it's very common that the class libraries or even the languages itself have an understanding of what concurrency means and what threading means, and that you can find different functionalities, thread-alike functionalities, also in the high-level languages. Especially in the Java world and in the .NET world, there's a lot of API, a lot of implementation in the class library that not only gives you basic synchronization primitives, as with the mutexes, but also data structures that can be used from different threads in parallel without running into race conditions. During the execution of these threads that you create, for example, in Java, the common model today is so-called native threads. So each of the Java threads or each of the .NET threads you create in one or the other way is mapped one by one to an operating system thread. This leads to very, let's say, good exploitation of the parallel resources. So whatever is there in terms of processing elements, multiple cores or multiple processors can equally be used either by a native programming language or by a managed programming language. So Java threads are completely equal to the creation of threads in POSIX, because this one-by-one mapping makes sure that the operating system still puts all your different threads on the different cores and processors in order to use all the resources. One interesting side aspect of multi-threading in standard shared memory programming languages is the question of whether threads are part of the language specification or if whether threads are only an add-on as part of operating system functionality you can use. So in standard C language, as an example, pthreads is basically an API you use that is implemented by the operating system. So the C language in itself has no concept of threads or concurrency. And the other example would be something like C++11 or even Java, where you have threading and concurrency as inherent part of the language. So there are constructs in the language that specifically deal, for example, with the synchronized access to data. And if you have this, then the typical situation is that you have a better definition of what is going on in your software when you have different kinds of parallel executions on the hardware. So in modern languages, such as C++11, it's very common to introduce concurrency as an explicit part of the language, which gives you the possibility to deal with multi-threading in a more predictable way.